Welcome everyone to the breakout session with Andrew Brereton. Andrew is a senior computational scientist currently working at Cyclica, a biotechnology company that is building the biotech pipeline of the future for drug discovery. Some of his achievements there involve building out a predictive engine that predicts the properties of potential drug molecules and also using machine learning to uncover novel biological targets. He completed his PhD in biophysics at the Oregon State University, where his research was focused on mining the PDB to uncover more about protein geometry and dynamics. He's also passionate about modeling and writing open source software for bioinformatics. It is my great pleasure today to introduce him to the screen, in which he will be presenting today about entropy and its role in understanding and modeling invisible systems. So feel free to take it away, Andrew.
Thanks, Rachel. So first of all, thanks everybody for having me here. This is going to be a pretty casual presentation, so drop any questions or comments in the chat as we go. And let's just dive right into it. So what I want to talk about today, I'm going to be talking about the importance of explicitly considering entropy when you're modeling things. And in the title that I gave Rachel, I said modeling invisible systems. And what I mean by that is really like when we're modeling things, especially if we're doing data visualization, as humans, we're often thinking about how things look and imagining what that means. But usually those are things where they don't even have, like they're at such a small scale that they don't even have a visual appearance. They're small. They can be smaller than the wavelength of visible light. So when we deal with these systems, it can be really easy to lose track of the fact that really we've got models acting on models. And the focus of this talk is kind of trying to get a framework for how to actually discuss these concepts and these issues. So AI itself is all about modeling. Arguably, it's all about similarity. But you're either modeling a behavior through the AI model itself, or you're modeling a behavior when you describe the data for the AI, or both. This is a quote that I really, really like. And I think this really cuts to the core of the modeling problem, which is basically if there's this sort of open question of what is a cat, and Norbert Wiener said the best material model of a cat is another, or preferably the same, cat. So by this, he means specifically that the more descriptive your cat model is, the better it is at describing a cat, the closer it becomes to actually just being that identical cat. And that poses a problem for us because the model itself stops being useful, basically, as it gets too complex. And all of this ties back to Boltzmann's principle for defining entropy. So there's a lot of different ways that you can define entropy. If you have a physics background, you probably think of entropy as it pertains to the second law of thermodynamics, which says that, entropy in a system must always be increasing. If you're a computer science background, you might be familiar with entropy in the sense of Shannon entropy or informational entropy. What people often don't consider, however, is that it's the same entropy, effectively. You can describe it conceptually many different ways, but ultimately it is really the same entropy and it behaves the same way in all of these different systems. So it's just a matter of choosing a framework for describing entropy that actually is useful compared to one that is, quote, correct. So here I want to talk about one of my favorite interpretations of what entropy is and how you can define it or measure it, which is specifically Boltzmann's principle for defining entropy. So Boltzmann loosely defines entropy as the number of microstates that are compatible with a given macro state. So in particular, Boltzmann was talking about chambers of noble gases. so here we've got, on the left, we've got this container that I've drawn extremely accurately and with high fidelity of a bunch of atoms moving around. Basically, these are, we can imagine these are, say, like neon gas atoms moving around in this chamber. And each atom here in this chamber has a position in the chamber, and it also has a force vector that's describing its momentum and its direction, essentially. This is a microstate, basically, for this container compared to the macro state, which could be, say, a temperature. So if I were to say this is a 2-liter gas tank that is full of neon and it's 13 degrees Celsius, this is a summary of this. It's a summary of this container. And essentially, if all I were to do was give you the temperature, in fact, there would be multiple different microstates where they're all compatible with the same macro state. So here, all of these arrows are the same. So it's the same number of atoms. It's the same speeds for all the atoms. It's the same momentums for all the atoms. So the temperature of this container should be the same. However, in this one, it probably would be the case that, half of the tank would be cold and half the tank would be hot. But in general, basically, with this temperature measurement, it's a summary. Information has been discarded in that you're unable to go backwards from this macro state of temperature to the particular microstate, which was the actual one that led to the summary in the beginning. So here on the screen, I'm displaying another microstate, basically. Does anybody want to take a stab at guessing what this is? Well, there's nobody typing in the chat, so I'm going to assume that nobody could tell that this was a drawing of the Mona Lisa. And I don't blame you, because what we're seeing on the right here is the text-encoded SVG format representation of essentially the same information that we're seeing on the left. Now, there are some small differences because technically, this is just pixels displayed on a screen, whereas this works at any scale because it's vector-based. But essentially, these are just two equivalent representations of the same information. However, the difference is when we look at this as a human being, we have a very, very hard time intuitively summarizing this and understanding it. Whereas when we look at this, we immediately can come up with a host of high entropy summary states that essentially define what it is and allow us to communicate about it, talk to each other about it, model it. So here, for example, we can summarize this by saying this is a clip art drawing of the Mona Lisa. Now, this once again shows the drawback of increasing entropy in this way. If I were to tell someone, show me a clip art drawing of the Mona Lisa, and I don't give them any extra information, these are all clip art drawings of the Mona Lisa. They all equally satisfy the macro state, which is this summary, but only one of them is actually the correct microstate. However, if you're just being given this, you have no way of knowing which microstate is the correct microstate. So this really applies to everything, not just clip art drawings of the Mona Lisa. So here, we can talk about proteins, for example. In protein science, we often talk about the primary structure, the secondary structure, the tertiary and quaternary structures. The primary structure of a protein refers to the linear sequence of amino acids that composes it. The secondary structure refers to whether these amino acids in the backbone form a helix or a beta strand or what have you, a turn. The tertiary structure is one of the, at least one of the folded 3D conformations that this protein can adopt. And then quaternary is really just referring to how this protein structure interacts with other protein structures. Now, interestingly, these are all equally accurate representations of this protein. It's tempting to say that, this is more accurate than this because this has more information. However, that's not the case. The accuracy really is the same. It's just that this is very, very precise, whereas this has much higher entropy because, for example, here we're talking about this, this amino acid, which could be in any number of individual three-dimensional conformations. So if I were to just give you the sequence, you can't really, even with AlphaFold, you can't really go to the correct microstate that's associated with this macro state. So while these are all equally correct, there's a clear flow of entropy that defines essentially which is a more summary type description, essentially, which descriptions have higher entropy, and that can be estimated by envisioning this flow of information where you can ask yourself, like, can I go backwards? Can I go backwards from this to this? Yes, because you can just look at the sequence that's here and then write it down, and that gets you perfectly to the primary sequence. But you can't really go from the primary sequence to the tertiary sequence, and so on. So here, it's not just about entire protein structures. Like, really, the key thing to think about with this concept is that it's at every stage that you're describing anything that you're working with, no matter what it is. So here we're just taking a very small fragment of this protein structure, and I can now summarize this and say this is a 15 amino acid long alpha helix. This has high entropy. This has low entropy. However, just because this has low entropy doesn't mean that it's more correct or better. In fact, it can be overspecified, because it's important to remember that this itself is a model. Like, this model of this protein structure is being built from measured data, but the measured data does not tell you specifically this is where everything is and exactly what it looks like. You actually have to do analysis, and you have to build this conformation, this model of a particular conformation, and there are errors associated with that process. There's noise, there's errors. So you're ending up with a low entropy model, but that means that there's also more opportunity to be incorrect. But ultimately, that's why the question of which is more accurate or which is more correct ultimately is not as interesting as asking the question, which model is more useful? And importantly, the answer to the question, which model is more useful, is always going to be subjective. It depends what you intend to use the model for. So as an exercise to really get this concept across, I'd like for you guys to tell me what the weather will be tomorrow. And I want to see who can come up with the most accurate prediction about the weather tomorrow. Just drop anything in the chat. Raining. Siri says it's going to be raining. Snowy. Super cold in Waterloo. Cloudy. Okay, perfect. Thank you, guys. Okay, so let's dig into these answers a little bit. So first of all, we've got raining, we've got snowy, and we've got cloudy. So of the three of these, which do you think is most likely to be correct? Assuming you don't know anything at all about the weather tomorrow, just on the basis of these predictions and the entropy that you think that these predictions have. A combination of all of them. Raining was said twice. So yeah, that's a good point. Like, if you're going to go by sort of like a data perspective, you could try to collect all these predictions and say like, oh, well, raining was said very often. However, there's a much more straightforward answer. Yes, Quinn has got it. That's exactly correct. Cloudy is more likely to be correct because clouds cause all other precipitation. So if it's snowing, it's cloudy. If it's raining, it's cloudy. So cloudy is a much less specific prediction, and also more likely to be correct as a result. However, we also had a prediction here that just said super cold. That's similarly very high entropy as a prediction. It's not even a certain temperature. It's a subjective prediction that it will just be super cold. It's also very likely to be correct compared to, say, a prediction where someone said, I think it's going to be, -5 degrees precisely between 1 p.m. and 2 p.m. Okay, well, thanks for giving me some weather predictions. Let's hope we actually get nice weather. Now, to give an example, though, I have the last few slides I have here, like they're kind of about specific examples. This one in particular is kind of interesting to me. Okay, I don't have an image slide for this, but basically, there's an AI company that I'm not going to name right now, but basically they used a data set of ligands that are bound to proteins called the DUD-E data set, and they trained a model based on this. And what this model was supposed to be doing was predicting if a drug that was being shown interacting with a protein was good, basically, like whether that interaction was valid or not. So that's what the model is predicting. It looks at a conformation that it's seeing, and then it says, I think this conformation is valid, or I think this conformation is not valid. So to train this, they described everything in very high detail. Like they position a model of the protein, they position all the atoms in the protein, they have the drug, they position all the atoms in the drug. They essentially create a very, very low entropy description, and that's the training data that they use to train their AI. However, then when they get their prediction out, when they make this prediction, basically they're making a prediction that is exactly the same amount of entropy as their training data. So when you train a model, you're basically taking your training data or reference data or whatever the case may be, and you're summarizing it, and that is the model. The model essentially is a higher entropy version of that data because the model is meant to predict the data. However, you can't go backwards from the model alone and recreate the data that was used to generate the model. So in the act of training a model, you're essentially increasing the entropy and creating a sort of summary. Now, the issue there arises when the prediction that the model produces is a configuration of atoms and a score associated with how good that exact configuration of atoms is. So essentially, they've created a model where we start with training data at a certain entropy, then we increase the entropy to create a model, and then the model is meant to, on its own, somehow magically decrease the entropy and produce a prediction that's now back at the same level of entropy as the original training data, which, like, quite frankly, that's just not possible. You can't, cheat the universe and just reverse entropy. You can't, make the correct information just appear out of the air, out of nothing, So one way that basically this was shown was you can actually just take this model that they trained and you can replace all of the drugs in the data set with just a single atom. And the result in the predictions that you get are actually exactly the same level of accuracy in terms of the metrics that they were using to measure performance, which basically indicates that what they thought they had taught the model to do, which was, learn from the data, summarize it, increase in entropy, decrease entropy again, produce a prediction. That's what they thought they had taught it to do. What they had actually taught it to do was just memorize the training data set so that you don't actually even need to look at the atoms in order to know what the prediction is going to be. So it turns out that the model wasn't violating any kind of physical laws about reality, and it wasn't reversing entropy. It simply didn't learn what the creators thought that it learned because that's impossible. So this is a case where like testing and considering and framing the problem really could have prevented this, because all you really had to do is realize that, you can't predict something at the same level of entropy that you're building your model from, essentially. So another example that I want to give, this is based on some work that I've been doing recently. So POEM, I've got a link here for POEM. I guess I can type this out in the chat if anybody wants it. / I did a link shortener specifically so that this would be typable. GUXHE. Okay. So this is a link to the POEM paper if anybody wants to read it. But POEM itself is, and I'm not going to go into this in this presentation, I guess, unless you guys have questions later or something. But POEM itself is really designed around this notion of increasing entropy deliberately and throwing out information, and that's how you get your prediction. And without going into that in too much detail, this ends up creating a restriction when you're using POEM if you're doing regression. And the restriction is that it can only produce a prediction that's as high or as low as the highest or the lowest value in the reference data set, which is equivalent to the training data. So what do I mean by that? Well, basically, like if you had a data set of 3 molecules, and it was a data set of solubility, basically like you're now predicting new molecules, the highest number that this POEM model could produce would literally be the equivalent of the highest number that was in the reference data or the training data, basically. So, oops, there we go. So this leads to an issue if you now want to do out of distribution predictions using this model, because if you have, you've got a model that's predicting, say, PIC50. This is a measurement of the affinity between a molecule and, say, a protein. And the higher this is, the stronger the affinity, basically. So the stronger, like, say, a binding event. And here we've got, the reference data, which falls along this range. Now, let's say we have a new molecule that we want to predict, but the actual measured value of this exceeds any of the value in the reference data. This point here represents the highest value that could actually come out of the model in terms of a prediction. So the question is, can POEM be used to make more potent molecules? If you're trying to use POEM to make predictions about the potency of a molecule, and you're trying to optimize this potency, how can you do that if you can't actually get a prediction that exceeds the data that you already know about? Anybody have any ideas? It's kind of a tricky question, and it doesn't require you to change the model. It just requires you to use it differently. So specifically what you can do is reframe the problem. So here you basically just have to, you're facing a limitation because the precision of the prediction that you're getting is too high. So you're getting these low entropy predictions out of this model because you're essentially saying, given molecule X that I'm trying to predict, what is its PIC50? Well, that's actually a very low entropy prediction compared to, say, is this molecule better than this other molecule, which is a much higher entropy prediction, because you're not saying it's better by exactly this amount, and you're not saying here's the values. You're just saying, yes, I think this is better than this other one. So now this enables us to reframe the problem of optimizing for PIC50, where instead of asking the question, can we predict the PIC50s of molecules? Here in blue, I'm showing the molecules that have real PIC50 values, which is on the x-axis. These blue molecules are the ones that have real PIC50 values that are actually higher than any point in the reference data. And then on the y-axis here, I'm showing the actual prediction that comes out of POEM. And what we can see is that even though the actual predictions that come out of POEM can't exceed the highest value in the actual data instead, what we see is, while we see that, what we also see is that in general, these out of distribution molecules tend to predict with higher values than the reference molecules. So now we can reframe the problem so that instead of asking what is the PIC50 of this molecule using our model, instead we can simply get the PIC50s, use that to rank all the molecules that we're predicting, and then we throw out the PIC50s because we know that they're not accurate, so we actually just don't use them. All we're using now is the rank order of these molecules, these blue molecules, and then it turns out that if you do that, you have a higher likelihood of being correct than incorrect, basically. So the model is useful for optimizing out of its distribution, but only if you throw out some of the output of the model in order to increase the entropy of the actual predictions. So that's the basic concept. And ultimately, like, what it comes down to is it's really important at all times to really consider, where is the entropy in my model, and where is the entropy in my system, and where is the entropy in my data? Because, if you're collecting data from somewhere, that's probably a summary of some sort of machine output, right? Like, for example, a fluorescence reading, being converted into gene expression levels. If you then build a model on those gene expression levels, you have to consider and keep in mind that those gene expression levels themselves are a modeled process based on an actual measurement that took place. And the measurement itself has some sort of entropy built in because there's an error that's involved in actually the machine that does the reading. So at every stage in your pipeline, you have to consider, where is the entropy that I know about, and where could there be entropy that I don't know about? And ultimately, you want to control this process as much as possible by framing the problem so that you can always know where the entropy is, so that it's not a mystery to you that will bite you in the ass later. Instead, it's something that you planned for and accounted for, and you're intentionally aware of it. So I just want to leave with some final remarks, and then we can just go to discussion and Q&A and stuff. But basically, this is another quote that I really love, and I think this also really sums up the situation, which is, all models are wrong, but some are useful. So just because a model is not accurate doesn't mean that it's not useful. And then likewise, it's never appropriate to view models of any kind. Even our model of, say, like how a chemical reaction takes place, that's still just a model of physical reality, which doesn't need to conform perfectly to our models. The second point here is just, when you're building models, ask yourself, how useful is this? So as you're building models, you're going to be tempted to say, like, I got to get these R squared values higher. I got to get, my mean error lower. I got to get my accuracy up, et cetera, et cetera. The most important question is always going to be, is this useful or not? And that's going to depend on how you intend to use it. And if you actually don't have an intended use for the model, why are you building it? You shouldn't be building it, because you're not building anything. You're just, moving numbers around for no reason. You don't need to discard data without a reason, but if you do have a reason to discard data, you should. There's a temptation to believe that, more is better, more information is better. But really, the work that goes into modeling is the act of discarding information, which is a concept called exformation, if anybody's interested. And then lastly, just test everything. You can never be sure. You can never be sure 100% that the model that you've built is doing or describing what you think it is. There's a large number of times, like the dude model that this other group made, for example, where you believe that you've got a model that's doing one thing, but it's only when you test it in very weird ways that you can discover that actually it's doing something completely different from what you expected. And that's it. So thanks everybody for listening to the talk. And if you have any questions, just drop them in the chat and we can handle it.
Yeah, feel free to ask any questions if you guys have. I know the expo session is starting soon, but definitely want to first get in any questions we have for Andrew.
All right, feels like that's probably right. Oh, does the point about changing entropy states apply to all fields of AI? Yeah, that's a great question. Yeah, all applications. Yeah, the short answer is yes, and not just AI. Like this is a general rule that really just applies to all models. Which, in a more general sense, I don't just mean predictive models, which is what we would usually call AI or machine learning. Or even just like statistics can be a type of predictive modeling. But even just modeling in general, which really includes any description of any system, essentially. And this ultimately, this is not just me asserting that this rule about changing different levels of entropy is always true and always important. This is really kind of the basis or one of the consequences of Gödel's incompleteness theorem, which is a mathematical theorem that basically shows that for any system, it will either be consistent or complete, but not both. And that's provably true. So if a system is consistent, that means that 1 + 1 always equals 2, and 2 + 1 always equals 3. And if A is greater than B and B is greater than C, A is greater than C. So that's what is referred to as consistency. Completeness would be like that everything can be known and there's no logical holes in the system that can't really be described. For example, like no paradoxes, essentially, no gaps in knowledge, no unprovable things or unknowable things. And because you can't have both, that means essentially that whenever you make a description or a model or a summary or even a predictive model, you have to account for this trade-off yourself. Like you're likely going to want consistency, which is always the case in like 99% of the time, which means that you're going to have to be aware that there are parts of the system that your model will be unable to accurately model. So for example, if I were making a predictive model that is, say, a neural net that predicts the solubility of molecules in chemical space, I train this model to do certain things. I can now predict, solubility, but it's going to be unable to predict maybe for certain classes of molecules because they don't have any resemblance to the training data or something of that nature. Like the temptation would be to think that because this is a model that supposedly operates in chemical space and does predictions in chemical space, that therefore the model is a model of chemical space capable of doing solubility prediction. But in reality, it's not. It's an incomplete model of chemical space. And if you don't know where those gaps are and where that incompleteness is, you're going to start producing bad predictions without being aware of it. So ultimately, whenever you're using AI, that's why it's so critical to try to describe where the entropy is in your system, wherever you can find it. And that would include like how the model is used, how the predictions come out, like what is the nature of the prediction? Does it just tell you, high, low, medium solubility? Does it tell you a specific value of like log solubility or whatever? And then also like how did you describe your data, right? Like where did the molecules come from? How similar are they to each other and what does that mean, by the way? I'll just drop that out there because whether or not two molecules are similar is an open question, right? Like consider like, what does that actually mean? If I were to say, like how similar is ibuprofen and acetaminophen? Like what does that actually mean? Like that itself is a modeled concept. There is no such thing as like true empirical similarity between two things. So any quantification of similarity, no matter where you encounter it, any system, if it's a quantification of similarity, it has to be a model and it has to be incomplete. So being aware of that is the only way that you can safely use those kinds of measurements, basically. And I mean, to consider like levels of entropy in similarity, in the example that I just said of like, ibuprofen to acetaminophen, you could say like at one level of entropy, you could say they're similar because they're both non-steroidal pain medications, right? But that's very unlikely to be useful. Like that's not really a useful summary description. There's almost too much entropy in that similarity metric because it just doesn't really matter very much for most of the things that you would want to do, right? But then you could try to do more complicated things like, oh, let's overlap every atom and measure the amount of, alignment between the atoms and the types of the atoms. But then you might be overspecifying things and overlooking the fact that for the thing that you're trying to predict, let's say solubility, all that really matters to you is like how many polar atoms are there versus non-polar atoms, or something like that. So whenever you're modeling, like the most effective predictive models will come from circumstances where you've chosen the appropriate level of entropy for your descriptions at every stage of the problem. And as a general rule, it should always be increasing. So every processing step that your model has, so like pre-processing the training data, formatting the training data, learning to create a model, then using the model to make a prediction, like at each step, the entropy should be increasing in the description that you're passing along, basically, because otherwise you're making stuff up. If at any point your entropy goes down before it goes back up again, that has to be made up. That is like to make the entropy go down, you will have had to impute false information because there's no way that you can just make correct information appear where it didn't exist previously. So that's the danger of not considering this when you're doing modeling. You have to basically be very, very careful that you're not accidentally imputing false information. Here's another kind of example of how that can occur without you realizing it. When you're modeling a protein structure, you have this data that you've already treated, you've already summarized and modeled it to get clouds that describe where electrons may be located. When you have a cloud in a certain position, you might say like the backbone goes this way, but in reality that could be an average of a conformation where the backbone goes in two sort of loops that are both like this, and the average is perfectly in the middle of them, and you've basically imputed this conformation that doesn't really exist simply because you weren't appropriately treating your initial data. Okay, so another comment from Lyle here. So know the limitations of the prediction abilities of your model and be careful of the features/data you're giving /know when you're giving it leading data. And anywhere we can go for recap more reading on this talk. Yeah, if you go to my website here and then scroll down to the bottom, there will be a thing that says articles on Medium, and there's one called when is AI trustworthy or something like that, and that goes into this concept a little bit more, but it's still fairly casual. And then in terms of giving it leading data, everything that you've said there sounds correct. I just want to caution that it's not just when you're giving it leading data, it's like at all stages of the process, you basically just need to consider like what kind of is my level of entropy at this stage, what is it at this stage, what is it at this stage, and if there's a sequence of events where information is being passed from one stage to another, you need to make sure that whenever that passage of information is occurring, it's always in a direction where entropy is increasing and never in a direction where entropy is decreasing. And that's going to be complicated, and it's going to rely on a certain amount of guesswork and intuition because you can't really quantify the entropy. Because if you did, you wouldn't even need to model the system in the first place. Like if you could quantify the entropy, that would be because you have a total view of the entire system. Essentially, you have the microstate perfectly. So yeah, I hope that kind of addresses your question, Lyle. Perfect.
Awesome. Thank you, Andrew. I found this conversation and this presentation really interesting, and it left me with like some considerations about considering entropy in modeling. So if there are no more questions, we can head over to the expo. There's some more industry booths and research poster presentations. For the research posters, we are having a prize at the end. So if you can vote for your favorite research poster, that would be great. And yeah, thank you once again, Andrew, for coming.
Thanks for having me, and thanks everybody for the questions and for attending. Have a great rest of your conference.
Yeah, you too.